Good afternoon, everybody. Firstly, of course, thank you very much to Professor Oak for the invitation to come and speak, and Director Kim for hosting us this afternoon. I'm also very grateful that you've left me some material to talk about. So, excellent introduction to biochar. So I'm going to talk about eco-resilience and how I see biochar having a part to play within that. A lot of what I'm going to talk about is to do with chemicals and contaminant interactions with char. But I thought I'd start off just with a sort of a conceptualization, if you like. So really, just to give it some framing with today's meeting and the idea of eco-resilience, which I see as being very much part of ecosystem service, so the functions that are delivered by soil. So I just put together this little diagram to try and summarize. So not everything that soil does and how char might take a part in that, but the things I'm going to talk about in the short talk today. So I think the first thing which is really important is how soil and char within a soil system has the potential to influence the hydrological cycle, to regulate water flows through the soil, change in porosity and the availability of that water and the movement of that water. The other thing which is really quite relevant to the talk that I'm giving this afternoon is how char and soils regulate the flow of chemicals. I guess a lot of what I'm going to talk about is to do with contaminants, mainly potentially toxic elements, but also things which behave like contaminants that we apply to soil on purpose. So pesticides, herbicides, those sorts of things. So soil and char have a role to play in regulating those flows. Together, both of those basically provide us with clean water, and soil does it naturally for itself. It's an ecosystem service that it provides. So I guess I'm interested in how we might augment that, make it better with char or with smart char. Major part of what I'm going to talk about in the material, in the lecture, is to do with those two things being put together. So how soils regulate water flows, how they regulate chemical flows, and how those then ultimately transfer to crops and to foodstuffs. I guess I'm very active in my collaboration with Professor Ju at CAS, so both acknowledged on the title slide. Now China has, as you probably know, really quite extreme problems with contaminated land. So recently, in the last 2 or 3 years, it was estimated that probably about 20 million hectares of land in China is tainted to the extent this agricultural land is tainted to the point where it shouldn't really be used for crop production. Now I think there's real potential, and hopefully the science that I'll outline will illustrate that, there's real potential to use chars and modified chars to abate that problem. And the solutions that you need for 20 million hectares of land are not high-tech solutions. They're low-tech solutions which make use of resources which are readily available. So quite a lot of the talk is about that. And then finally, I'm going to touch on this at the end of the material. The other thing which soils, and possibly char-amended soils, can do is to regulate the exchange of gases. It could quite simply be oxygen and carbon dioxide through respiration, but there are other gases which are probably more important, so nitrous oxide and methane emissions. Again, char potentially has a role to play within that. So hopefully that provides a bit of a framework, so when I talk through the science, you can kind of see this theme of eco-resilience, soil ecosystem services, the natural system, and what it is we're trying to do with char to augment that. Okay, so I'm going to start off thinking about soil pollutant interactions and various publications. So kind of to make it easy for everybody, I've sort of keyed these with whether or not it's a pot trial, the sort of plant that's been grown, in this case it's lettuce, and the sorts of chemicals that the study relates to. So the examples, I've got 4 examples that I'm going to draw from. They're all strong collaborations with IUE, Professor Ju and Chow Kai. This one unusually looks at organic chemicals. So PHEs are carcinogens, we've heard about those previously. A lot of peri-urban environments, because of coal power or emissions from cars, they're tainted with PHEs, which of course are a concern because they're carcinogenic. So this is a study, unusually, to look at organic chemicals rather than regular metals. The first couple of slides just look at biomass growth. And this study was basically a comparison between what happens if you apply conventional sludge as opposed to converting that sludge into char and then applying the char. Again, as Professor Ju highlighted, that char is quite a risky commodity in so much as tainted with heavy metals, it's tainted with personal care products, organic contaminants, and it has a pathogen load associated with it as well. So there's lots of advantages for converting that high-risk material into lower-risk char products. So just in terms of plant growth, what we basically see is that a small amount of sludge, the first set of bars, 2% addition, quite stimulating, the plants grow well, but as you increase the sludge load, then the metals, the toxicants start to depress the growth. For the char amended systems, we don't sort of see that effect. We see this uplift in biomass, and we maintain that uplift as we increase the char content. If we now look at the pH accumulations, these are these potentially carcinogenic chemicals. Again, we see a fairly marked effect that the organic amendments themselves, they reduce the pH transfer from the contaminated soil into the biomass. But as you increase the amount of sewage sludge that's applied, that level of pH starts to creep up again. So the sludge itself has a pH load, and as you increase the char load, that pH load starts to transfer into the crops. The char amended soils going from 2.5 to 10%. Again, we see this sort of leveling off, that the pHs have been basically destroyed when you produce the char, and so when you amend that char into the soil, you don't see this creeping up in the pH levels. Okay, so the second study I want to talk about, and this now is a bigger scale, so it's a greenhouse study. Again, it's looking at lettuce, but this time we're looking at metals, and cadmium is being the risk driver here. So this study, I guess, is quite, has a place in so much as the application of char in this study is really quite low. So these here are very low applications of char. This is probably of the order of about less than 0.5% char addition into the soil system. The level of elevation of cadmium within the soil on this greenhouse site is around about the regulatory limit. And you can see that when they grow lettuce in here, that it just tips over the regulatory limit. So we're looking for a low input of char, which is sufficient to bring the cadmium level down to below the regulatory limit without being really burdensome in terms of how much char you have to put in. So again, fairly successful, 18 tonnes per hectare application, and the cadmium levels in the lettuce are brought down to something that's safe. Obviously, this is a real commercial operation. It's generating food in a peri-urban environment, and that food's going into the food chain. So small intervention takes things to a place where the food is safer and below regulatory limits. Next study, so there's 4 of these. I'm just going to whistle through basically. Now we're changing scale again, so we've gone from pots to greenhouses. Now we're at a field scale. This is a field site in Hunan. Again, cadmium is the risk driver here, and we're looking at accumulation now into rice. Obviously, rice is a very important staple, whereas lettuce isn't. So again, it has its place to play. So if we look at the data on here, there's various metals shown: cadmium, zinc, lead, and arsenic. So if we deal with the other metals first, so there's no real effect from control to these char amended systems for zinc. Not really much going on for arsenic, not very much going on for lead. So these are all present at a background concentration. They're not elevated within the soil. The real risk driver here, mainly from the reuse of polluted industrial effluent as irrigation water, is a cadmium. We're screening 2 different chars, so bean straw char, rice straw char. And again, this is significant, the argument that you're reusing materials which are a problem, they become redundant, they're a waste. What are your options? Well, you could plough them back into the soil. They'll quickly be degraded and flux our carbon dioxide back into the atmosphere. So there's benefits, as Professor Oakes illustrated, to converting through pyrolysis these waste residues, sequestering carbon with them, burying it in the soil, and hopefully getting some benefit alongside that. So for the cadmium control to either the bean or the rice char amendment, we're seeing significant drops in the cadmium content within the rice. So we've got rice husk and rice grain, the same thing over here. Again, this kind of leads forward to how you might tailor chars. So these 2 different materials, for all they were made under the same conditions, the feedstock is changing how successful those amendments are at removing the cadmium, changing the availability of the cadmium and allowing it to transfer into the food. And I don't think we're really at the point now where you could advocate, hand on heart and say, okay, go make some rice char, put it in your cadmium-tainted soil, and it'll all be fine. Yeah? I think we're at the point where, there's ambiguity, and people could be making the wrong sorts of char and hoping that they're going to deliver the performance that they need. This is just sort of another way to look at the data. So over here, this is for soil. So we're looking at the availability, so weak electrolyte extraction. There's no control shown on here, so these numbers are all how the performance relative to the control. Okay, so we're seeing about a 2/3 reduction with the bean straw char and probably about an 80% reduction for the rice char. Obviously, cadmium is the risk driver here, but we do see changes for zinc, lead, and arsenic. They're at background concentrations. And then when we cascade that forward into bioaccumulation factors into the grain itself, in the rice, obviously we're getting the same sort of result we saw a minute ago. The two perform differently, but they make marked reductions. Background concentrations, they're not really influenced by the char addition. Okay, and then the final study, this now is for arsenic. So we're still with rice, but we've changed the driver, the risk driver is now arsenic. Arsenic is a massive global problem. It's one of the main contributors to these tainted soils in China. So it's a rice study with arsenic, but this time it's a pot study. Okay, so very briefly, because you're kind of getting the theme for things here, for the arsenic and for the cadmium, we're seeing significant reductions in the char amended systems, the grey bars over here. Again, linking into what other people have said today in a sort of holistic system, an urban system, reusing nutrients and wastes and things. These are sewage sludge chars. So rather than being waste crop residues, they're sort of human waste from sewage works, and they're being converted, say, to kill the pathogens, reduce the organics or destroy the organics, and lock up the metals within them. So I think this is a good study in so much as it's reusing a waste which has hazard associated with it, and it's bringing around really quite significant changes, in this case arsenic and cadmium concentrations within the rice grain. What we did with this data was to sort of propagate it forward and think about the inorganic arsenic health risks that are associated with that. So basically we looked at lifetime risks, purely based on the inorganic arsenic that was in the rice grain. We calculate there's about a 2/3 reduction in the cancer risk. And for me, this is, I guess, it's kind of a high point for our collaboration in the science that we've done, because we have evidence here that making really simple interventions with biochar materials makes big, meaningful differences to life cancer risks for people that are consuming tainted rice. Okay, so that's kind of the first half. There's 2 quarters still to go. The first of those is a different sort of tack. So one of the things I've been interested in historically is organic chemicals, be those pollutants or herbicides or pesticides. So a little bit of work here talking about how pesticides interact with char. Now, I guess I would add at this point, this could be for benefit, but it could also be detrimental. I'll come back to that in a minute. Okay, so this study looks at isoproteron. It doesn't really matter what the chemical is, and this is a herbicide. This was really, really popular in the UK and in Europe. It controls a weed called blackgrass, which grows in cereal. And farmers used so much of this, it got banned. Okay, so the groundwater concentrations went up, and the EU basically banned the use of isoproteron. But the weeds, the blackgrass, they continue to be a problem, and through quite a lot of lobbying and pressure, it's been reauthorized as a component within herbicide formulations. Anyhow, we did a little study here to see how biochar influences the partitioning and bioaccessibility of this particular chemical in soil. Very simple study, so microcosm study. We loaded them up with either a control, so nothing, recommended dose of this soil application herbicide, 5 times or 10 times the recommended dose. These are all carbon-14 studies. That's kind of one of the things we're set up to do in the lab. As they were either soil-only systems or soil plus 5% char, and then we let the chemical interact with the system for different amounts of time. All I'm going to present here is the extractability of the chemical. The paper is about the bioavailability and the microbial response to the chemicals, but I'll just talk about the simple stuff this afternoon. Oops. What's going on here? Okay, so anyhow, if we look at the data, this basically shows soil with recommended herbicide application, soil with char at the recommended dose, and then double the dose, 5 times the dose, and 10 times the dose. The white bars, they all give high extractability. So the isoproteron is a fairly mobile chemical, very, very extractable. But right at the beginning, day one, as soon as the chemical's been put into the system, there's an axis break here, about 2%, less than 2% is now water exchangeable. So it's made a massive difference to the chemical. You know, so you could argue, well, you could have rigged this study by picking a chemical that was quite, you know, amenable and would stick onto the soil or onto the char. It's a really quite soluble chemical, and the char still soaks it up very readily and very quickly. If we just sort of look through the data set, the same picture is always there. So running right up to 2 months, still there's hardly any extractability of the herbicide from the char-amended soils. And then the other thing you kind of see is that with time, oops, there's some craziness going on here. With time, we have high extractability in the soil, and it sort of gets a bit less, a bit less, a bit less as time goes on. That's what you'd expect these sort of chemicals to do. Right, I know what's happened to this, but let's persevere. Okay, so there's some column studies. All the stuff that's missing, don't know why it's missing, is isoproteron loaded onto the top of these soil columns, soil column, and then flushed through with various volumes of water, and then quite simply collecting the eluent at the end. Again, the data is quite marked for this. So if we look at the top of the curve, so here we've got soil-only controls and soil with a tiny bit of char in it, and you see basically all of it breaks through, 90% elution really quite quickly. If you look at the other end of the spectrum, so now we've got 5% char, either coarse or fine, doesn't really matter. Again, there's an axis break, none of the stuff's come out, it's all stuck on the soil. And then 1% to 2%, they basically occur in the middle. If you then go and slice up your core to see where the chemical's gone, this is basically what we see. So within the top 2 centimetres of the char-amended soils, we've got about 80% of the chemical is stuck at the top of the column. For the soil-only controls, obviously, it all fell out the bottom a minute ago, and so there's hardly any in the soil itself. Okay, so just dwelling on this for a minute, obviously there's a positive story here, that there's clearly opportunity to put char into a buffer zone, let's say, edge-of-field buffer zone, or to use char as part of a field drainage system. So when the pesticides try to leave the field through the drains, they become absorbed onto the char, and they could bring benefits. They would bring water quality benefits at the end of the day. But if you're sort of being savvy and thinking about this, the implications of this and the lack of availability of the herbicide on the other slides might suggest that char-amended soils have the potential to soak up chemicals and stop them from working. So we've done some other work looking at deactivation of herbicides, and again, if you put in enough char, then you soak up the chemical so effectively that it no longer kills the target weed species. Okay, so for all I've presented quite a positive picture, I think it's useful to be pragmatic and think, well, what's the application scenario? Are there opportunities for negative impacts to be generated? Okay, the final thing I want to talk about, so you remember the first slide that basically talked about water flows, talked about removing pollutants from soil, implications for food safety, so I've kind of covered most of the introductory slide. The last thing I want to talk about is the nitrogen cycle and modified chars. I really think, Professor Oak has said, that the direction of travel for chars is to try and predefine or engineer what the application might be. As you've seen in the previous data, sometimes the chars work, sometimes the chars don't work. And I think we can't just blindly go forward making char and using any char for any application. The skill is going to be in identifying traits of the char and making char which has that trait and then using it for a particular application. Okay, so this is new and exciting. Sharpen your pencils. To my knowledge, no one's made any copper modified char, and you might be wondering why would you want to do that. Okay, so some unpublished data and some ideas for you here. Complicated diagram, but the point I'm trying to make here is that as we design our chars, I think we really have to have in mind what that purpose or function of the char might be. And on this horribly complicated diagram, which basically looks at different parts of the nitrogen cycle and different players within that, it identifies key enzymes within here, like these NIR enzymes, NIR-S and NIR-K, and these NOS enzymes like NOS-Z, which are really important for how we change nitrate through to nitrite, nitrous oxide, through to N2 at the bottom of the diagram. So my motivation for making copper-amended char, if you look at the key here, the purple dots, all of these enzymes are copper-dependent, 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 all of them are copper-dependent. So one of the things that's emerged in the literature is that if you put char into a soil, sometimes nitrous oxide emissions go up. Soils get wetter, they hold more water, the microbiology responds. And so while you've stored carbon in the char, and Johannes is already excited, we've stored some carbon, it's great, you have this negative feedback that you've undone the good work by pumping out a really potent greenhouse gas as a result. So the idea here is, why not make char that will safeguard against that? So your char can store its carbon and it can remove copper limitations and pull the denitrification through to give N2 gas at the end, rather than having nitrous oxide emitted from the char-amended soils. So these few slides say it's not published, it's kind of hot off the computer, if you like. So we've got controlled soils over here, increased biomass from char or copper-amended char, so that's a giver. Over here we've got nitrogen, oh sorry, it's grain mass, so increased yield of grain, and this is nitrogen uptake efficiency. So again, there's a lot of concern in the world about our use of nutrients, inorganic fertilizers, and here's quite nice evidence that at modest nitrogen fertilizer application, we get much more efficient use of that chemical in the char-amended and the copper-amended char systems. And then to close this out, if we now look at upregulation of NOS-Z genes, so these are the genes that pull nitrous oxide, N2O gas, through to N2, we can see upregulation in both the char-amended chars, the copper-amended char, sorry, which doesn't exist in the regular biochar itself. This particular study, I would say, a little bit limited. Master student did this. So we're seeing over here, we're seeing controlled char given as a bit of a nitrous oxide flux, whereas the regular char and the copper char, again, there's not really much in it, and there's a bit of variability on here. But I think we have the first step in terms of an innovative modified char, and with the application of that being to regulate nitrous oxide emissions from amended soils. So I'm quite excited about that. I think it's a good opportunity for some collaboration here with Professor Oak and Professor Jew. Paddy systems, obviously ideal candidate for this, and I'd really love to upscale this to look at a field scale sort of experiment. The end. Thank you.